We live on a planet that breaks records for the diversity of life forms. From snow-capped mountain peaks to vast oceans, from microscopic bacteria to giant whales, Earth seems overflowing with life, a paradise. But how typical is this picture in the universe? How commonplace is life? Is Earth really a rare exception to the rule? Or, on the contrary, is life the cosmic norm, and we just don't know how to find it yet? The question of the existence of extraterrestrial life is one of the most fascinating, fundamental and important questions humanity has ever asked in its history. It is a question that touches not only science and technology, but also philosophy, religion, and our understanding of ourselves. Today we will venture into this fascinating and complex debate by comparing in detail to polar and often contradictory viewpoints. The Rare Earth hypothesis formulated in the book Rare Earth by Donald Brownlee and Peter Ward, and the alternative hypothesis of life everywhere. The Rare Earth hypothesis is not simply a claim that life is difficult to arise. It asserts that the conditions necessary for complex life, multicellular organisms, animals, intelligent beings, to arise and be sustained are extremely, almost unbelievably, rare. It is not a question of if but rather a question of when and where. Proponents of this hypothesis emphasize that the emergence of life is one thing and evolution to the level of complex intelligence is quite another, requiring unique circumstances. This requires not just the presence of a planet in the habitable zone around the star, where water can exist in liquid form. It requires a whole cascade of coincidences, an almost unbelievable confluence of astronomical, geological, and biological factors. Imagine the combination of a safe lock with thousands of numbers. The odds of all the numbers coinciding by chance are slim to none. And perhaps our Earth is the only example of the realization of this scenario in the entire observable universe. Recall that Earth had a colossal collision with Theia, a Mars-sized protoplanet that led to the formation of the Moon. It is not just a beautiful satellite, but a stabilizer of the tilt of our planet's axis of rotation, providing temperate seasons. Without the Moon, Earth would have chaotic climatic conditions not conducive to complex life. Or the so-called Big Bombardment, a period of intense bombardment by asteroids and comets that nearly destroyed any nascent life. Earth survived, thanks perhaps to the unique gravitational defenses of Jupiter and Mars. Our galaxy is a turbulent place, but we are in a special region of the Milky Way, on the outskirts of the galaxy, far from the intense radiation of the galactic center, from supernovae, and from dense regions of gas and dust. This galactic suburb may be critical to the development of life. Jupiter, as a huge gravitational shield, pulls comets and asteroids away from us, preventing catastrophic collisions. Mars, on the other hand, holds back the asteroids of the asteroid belt. But it is not only the presence of giant planets that matters, but also their precise location and stable orbit. The presence of liquid water is a prerequisite for life as we understand it. The Earth is in the so-called habitable zone around the Sun, where the surface temperature allows water to exist in liquid form. But the habitable zone is not just the distance from a star. It is also the stability of the star itself, its radiation and age. Plate tectonics is not just the movement of continents, it is a complex mechanism that regulates the Earth's temperature, providing the carbon cycle necessary to maintain a stable climate and keep carbon dioxide concentrations at optimal levels. The Earth's magnetic field is an invisible shield that protects us from solar wind and cosmic radiation, which can be devastating to DNA and living cells. Not all planets have a strong magnetic field, and the Earth is an exception in this sense. The Moon, as we mentioned earlier, plays a critical role by stabilizing the tilt of the Earth's axis of rotation, which in turn provides the predictable and temperate seasons necessary for the development of complex ecosystems. Without this massive satellite, whose gravitational force holds the Earth together, our planet would likely be an unstable and completely unpredictable place, unfit for life as we know it. Photosynthesis, carried out by plants and algae, saturates our atmosphere with oxygen, a gas necessary for complex life to breathe. The oxygen catastrophe that occurred in Earth's past created the conditions for the emergence of multicellular organisms. All of these factors combine to create a unique environment on Earth that has allowed complex life to not only emerge, but to thrive. Proponents of the unique Earth hypothesis argue that finding another planet with the same set of favorable factors is a nearly impossible task. But let us look at an alternative viewpoint, The life everywhere hypothesis argues that we take too narrow a view of the possibilities of life. We look for Earth-like planets, but what if life could exist in completely different environments that we can't even imagine yet? We find life even in places where there should seemingly be nothing living. Extremophiles, microorganisms living in boiling acid springs, in Antarctic lakes beneath the ice, in radioactive waste, show remarkable resilience and adaptability. This suggests that life may be far more versatile and adaptive than we originally thought. Perhaps life is not based on carbon and water, but on other elements and solvents. Proponents of this hypothesis claim that the universe is so huge, billions of galaxies, each of which contains billions of stars. Each star, on average, has several planets, even if the probability of life on a single planet is extremely small. On the scale of the universe, the number of planets inhabited by life must be enormous, unless there is some global filter preventing the development of life. We are constantly expanding the horizons of our knowledge by discovering new exoplanets, many of which are in the so-called habitable zone around their stars, potentially suitable for the existence of liquid water. Moreover, we are increasingly finding indirect signs of liquid water and even organic molecules on the satellites of giant planets, Europa, Enceladus, Titan. This suggests that life may exist not only on Earth-like planets, but also in subglacial oceans, atmospheres of gas giants, or perhaps even in the acid clouds of Venus. So which is more likely, based on the knowledge and data we have? A rare Earth, a natural wonder resulting from an incredible coincidence, or life thriving on multiple worlds, simply hidden from our view because of vast distances and our limited capabilities? The arguments in favor of the unique Earth hypothesis, voiced in particular by the authors of the book Rare Earth, consist in the emphasis on an extremely complex and finely balanced combination of factors that together make the Earth ideally suited for the emergence and sustainable development of complex life. Proponents of this hypothesis consistently emphasize the extreme rarity of each of these factors, as well as their close interdependence, creating a kind of domino effect where the absence of even one element can lead to the collapse of the entire system. The arguments in favor of the life everywhere hypothesis rest on the astonishing variety of conditions in which life has already been found on Earth and the truly astronomical number of potentially habitable places in the universe, which, as new exoplanets and satellites of giant planets are discovered, continues to grow. Moreover, the existence of extremophiles on Earth, adapted to the harshest conditions, clearly demonstrates the incredible resilience and adaptability of life. Proponents of this hypothesis argue that we must radically expand our ideas about where and how life can exist, revise outdated paradigms, and consider the possibility of life based on completely different principles than those we observe on Earth. The question of the Earth's uniqueness and the prevalence of life remains open, and we may not have an answer until the distant future. But the search for this answer is a journey that enriches us with knowledge, broadens our horizons, and makes us think about the most fundamental questions of existence. Regardless of what we discover, this search will lead us to new discoveries and new knowledge about the universe and ourselves. So let us keep exploring, searching, and dreaming of what lies ahead.